So we're now going to start talking about Semaphore, which is one of the core Java synchronizers along with reentrant lock and condition object that we'll be covering in this course. We'll start off this lesson by discussing what is a semaphore, and we'll talk about a couple of different types of semaphores, counting semaphores and so-called binary semaphores. And as is my tradition, I'll also give you kind of a fun, memorable example of the human known use of a semaphore that shows up in practice. So a semaphore is conceptually an object that can be incremented and decremented atomically in order to control access to some shared but limited resource or resources. And you may wonder, why do I have these funny like signal flags here on the slide? And the reason is very simple. That's one of the places where the concept of a semaphore came from in the first place. Semaphores have been around for a long time. They're one of the early synchronization mechanisms that was defined probably 40, 50 years ago. And originally, the concept was inspired by the way in which railroad trains share a common track. And the idea is that you've got these signal flags that say stop or wait, and then you have another flag that says clear or go. And that's, in fact, why they used to call semaphore operations P and V. They were from, I think it was Dutch. And I believe Edsker Dijkstra was one of the first people to document semaphores, and he was Dutch. So he used P and V as the names. We have more intuitive names now, like acquire and release, which is more sensical to people who are not Dutch. So the idea here is that you want to make sure that two trains aren't on the same shared track at the same time, especially if they're going towards each other. And so you can use these signaling flags as a way to keep track of who's going and whether or not something's already in use. Concurrent programs in the software world, not the train track world, use semaphores to coordinate interactions between multiple threads. And we're going to, again, use a somewhat whimsical example here to illustrate this point. And we're going to basically share bottles of wine. And you might wonder why we're using that crazy example. And if you watch the link at the bottom of the slide, it's a Grateful Dead song, which talks about sharing. And so I'm not espousing consumption of alcohol. I'm simply showing an example that uses a Grateful Dead song as the motivation. So we have some Grateful Dead wine, and we want to share it effectively. And here's basically how this is going to work. We're going to start out with a count of the number of resources that we have. In this case, it's going to be bottles of wine. And we're going to start out with 3 because we have 3 bottles of wine to begin with. And then we have a bunch of threads or people who want to consume the wine. And every time someone wants to consume some wine, they come along and they check to see what the count of the semaphore is. And in fact, what they do is they try to decrement that count by 1. And if the count is greater than 0, then they get the resource, which in this case is a bottle of Grateful Dead wine, and then they can go and consume some of it. And this keeps happening as long as the count of the semaphore is greater than 0. That means people can come along and get access to the underlying shared resource. So another thread, another person comes along, decrement the count by 1, go off and consume some wine. And then the third thread comes along and they decrement the count by 1. So at this point, all the bottles of wine are now being shared. They're being used. So when any other threads or another person comes along and they want to get a bottle of wine, well, at this point, they're all being shared by other beings, other threads, other people. And so in this context, anyone who comes along later when the count of the semaphore is 0 is going to have to wait. And typically what happens is they will go to sleep because they're very tired and they need their wine. Actually, wine would probably make them even sleepier, but forget about that. The analogy only goes so far. So at some point, someone's done having a glass of wine or having part of the bottle of wine. And because they're good citizens, they're going to share and they're going to put the bottle back, perhaps with less wine in it at this point, and that will atomically increment the semaphore count by 1. And at the point when the semaphore count is atomically incremented by 1, that means that some waiter thread, somebody who's waiting for the count to become greater than 0, can then wake up, and then they can go ahead and perhaps acquire that resource and consume some of the wine. This particular example of semaphores uses a fully bracketed model of acquisition and release, namely the the thread that acquires the semaphore is the same thread that releases it. That is not always the way you have to do things with semaphores, as we'll see shortly, but that's the way we're doing it for this particular example. Keep in mind that with reentrant locks, you have to follow a fully bracketed model of acquire and release. Well, let's turn on ourselves to the next topic related to the concept of semaphore. And here we're going to talk about the two different types of semaphores that are available. One type of semaphore is called a counting semaphore. And as the name suggests, it keeps track of a number of permits, which can be greater than one. And this is essentially the count. It's the permit count, as they sometimes call it. So the permit count with this counter, which can go to n, has a very precise meaning. If the current count is negative, that means that many threads are queued up waiting to acquire the semaphore because it's already been used. It's like there's no more bottles of wine, so you have to wait, and that keeps track of how many waiters there are. If there's zero, if the count of the semaphore is zero, it means there's nobody waiting, but it means that an acquire operation is going to block until the count becomes positive. And then the third type of state that the semaphore can be in is a positive number, which means that not only are there no waiting threads, it means that if someone wants to acquire the semaphore, then they won't block because they'll simply atomically decrement it by one. Now, keep in mind, this is conceptual. When we actually do an implementation of semaphore, we might choose to implement it in such a way where the count actually doesn't ever go negative. But that really is an implementation detail. And we'll talk more about that when we get further along. So a counting semaphore can basically be used to keep track of how many resources are available. A binary semaphore, in contrast, is essentially an all or nothing thing. And in a sense, a binary semaphore is sort of like a reentrant lock with a few other extra things, like you don't have to follow the fully bracketed protocol. A binary semaphore, as the name implies, has only two states: acquired, in which case the count is zero, and not acquired, in which case the count of the semaphore is one. That's why it's binary. So basically, we're restricting the count n to either be 0 or 1. Now, in practice, binary semaphores are often implemented using counting semaphores. So you can implement a binary semaphore as long as you follow a strict protocol where you never have the count be greater than 1 or less than 0. We're going to talk about a number of examples of counting semaphores and binary semaphores here in just a little bit. But don't worry, we'll cover that stuff, but we're not going to go into the examples quite yet. The short description, the short synopsis, the Cliff Notes version, as it were, of these two concepts is as follows. So the Palantiri simulator app, which is what you're using for your assignment, uses a counting semaphore. And this demonstrates the fully bracketed model, much like the Grateful Dead wine example we looked at before, where the thread that acquires the semaphore must be the same thread to release it later. We're also going to talk about other examples like the ping pong app, which uses a pair of binary semaphores. And we'll talk more about that later, and I'll probably get a chance to walk through the code because it's a fun example that demonstrates various interesting ways in which you can use not just semaphores, but other synchronizers in order to coordinate alternating action between a pair of threads. And so the way that this app works is we have two threads and they take turns either printing ping or printing pong. So therefore it's a ping pong app, and they alternate and they use a pair of binary semaphores to acquire and release and coordinate their interactions. This particular example demonstrates non-bracketed semaphores. So it's a little different from the fully bracketed model we see with the Palantiri simulator app that you're using for your assignment. Well, I promised you I would have a human-known use of semaphores, and I always get a kick out of this because it reminds me nostalgically of my days as a graduate student many years ago. So I went to grad school at University of California, Irvine, which is right on the Pacific Ocean coast. And so people spent a lot of time sailing and swimming and playing beach volleyball. And so the particular example here is something that I saw quite frequently when people would go out to play beach volleyball at some of the fantastic beaches along the coast, like Corona del Mar. And the way it worked was you would typically, on any given day, especially on the weekend, you'd have a whole bunch of teams that wanted to play beach volleyball, but there were a limited number of beach volleyball courts. So to coordinate things, there would be sort of a station, like a lifeguard station, that would keep track of the available courts. And the way they did it was they had a bag full of beach volleyballs. And the protocol was if you wanted to play on one of the courts, you had to go over and get a volleyball from the bag of volleyballs. Well, if there was a volleyball in the bag of volleyballs, that meant that there was an available court. And so someone would send a representative over to look and see if there was any balls in the bag. If there were, then they would go ahead and take one and go off and play. And when they were finished, they would come back and replace the volleyball in the bag of volleyballs. If you showed up and there was no volleyballs in the bag, then that meant that the courts were all in use. So that was an indication in a semaphore-like way that all the resources were currently occupied or in use, and therefore there were none available at that point. And so you'd have to sit around and wait your turn in order to be able to go and play. So that gives you a very simple example that I always remember about using semaphores or semaphore-like concepts in order to coordinate the actions of multiple parties, in this case, multiple teams of volleyball players, or could be threads in our case, in order to be able to share some resources effectively and efficiently. So that's the end of the introduction of semaphores. We will now start talking in more detail, of course, about the technical aspects that underlie this important synchronization mechanism.